and bounded. Then use the monotonic sequence theorem to determine whether the sequence converges. So again, I'm going to look this one up because I don't have all these off the top of my head. All right, so okay, so an increasing or decreasing sequence is called monotonic. And I guess I don't remember if we write out a few terms here. If n equals 1, it's 1/4. If n equals 2, it's 2/5, and so on. N equals 3, you get 3/6, right?
Mm-hmm.
So this one is, well, that's 0.25, that's 0.4, but that's, did I misdo this? No, n equals 4. Sorry, this one looks like it might rise before it falls. Let me just graph it real quick.
Okay.
Yeah, it does. That's weird. No, I'm sorry, it is increasing. It goes, see, the limit is 1. Okay, yeah,
Right.
because this becomes 4/7. So it's actually increasing. Well, yes, 0.25, 0.4, 0.5. Yeah, it's actually increasing. And I don't know how you have to say that, but that's what monotonic means. I mean, it's either increasing or decreasing.
Okay.
So then the next one is whether it bounded or not. So we can say that this thing is always less than or equal to 1. And I don't know if we have to say any more than that, but that's the bounded part. Basically, it's less than a number everywhere, and this is the upper bound. And how did I get that? Well, if you write it out a few more terms, you'll see that. But basically, as n gets large, n plus 3 goes away. It's just n over n, which is 1.
Right.
Right. And then determine whether the sequence converges. So again, it's the sequence, not the sum. It's the sequence. And we can say we can say that it does converge to 1.
Okay. What's the difference between seeing if a sequence or sum converges or diverges?
Well, like the sum of this would be much harder to figure out. The sum of n over n plus 3 is like adding all of these little ones up. Whether actually this part right here converges is different. It's like, do the numbers approach a value? So like this one would fail the divergence test. Because the limit as n goes to infinity, n over n plus 3 equals 1, which does not equal 0. So it immediately fails that.
I thought if it didn't equal 0, then it diverged.
Yes. So I'm sorry. Well, okay, depends on the wording here. So the divergence test says that if it doesn't go to 0, then it diverges. So this one diverges. The sum diverges.
Okay.
But the sequence itself, it converges to 1.
Right. Because it's getting closer and closer to 1.
Yes. Yes.
Okay.
So something that is neither bounded nor converges would be something like cosine of n over n. Well, that's not a good example. Cosine of n over sine of n, maybe. Because cosine and sine sit there and they bounce between -1 and 1 and -1 and 1.
Mhm.
So you never know whether it's 1 or -1 or undefined or even 0. Like it bounces around.
Right.
And so it's not bounded because it approaches two different things. It's not monotonic either. So the reason the monotonic is really important is because if something is, and the decreasing is the more common case. If it's decreasing, it tends to approach a value, usually 0. Usually that's what we're looking for.
Okay.
But if it's increasing, you got to be careful. Like it could be increasing to like 1/2, and that's good. But if it was increasing to like 1, that's bad because it would not converge. The sum would not converge, but the sequence would.
Oh, okay. Okay, I get what you're saying.
Yeah. And so like I understand, like it's like if as soon as I put a sigma in front, like this thing diverges, but
Right.
there is no sigma, so you don't have to worry
Right.
about that. And that's why it says the sequence, the sequence, the sequence. Okay, 16.
Yep.
Okay. Definitely going to look for a reference on this one. I remember, I think you have to prove that a P series is that this one here, 1 over X to the P.
Yeah.
Okay. Okay. So A to infinity. I don't know what it means by prove here, other than like if you find the antiderivative of this, which is if you recall, this is really integral X to the minus P. Okay. You add 1 and you divide by the new exponent. Okay. And then you evaluate from A to infinity, and you take the limit. Actually, we're gonna put a B up here. The limit as B approaches infinity. And then you put in the 2 bounds. So it's X minus, well, actually, let me rewrite this because it is a little wonky here. So it's better to write the bottom as 1 minus P. And then same thing with the exponent X to the 1 minus P. That's sort of how I guess it's seen
Okay.
in maybe books here. And then you put in the bounds. So you go 1 over 1 minus P, B to the 1 minus P, minus 1 over 1 minus P, A to the 1 minus P. And you got to take the limit as B goes to infinity. And this is where if P is greater than 1, this over here on this B to the 1 minus P, you can imagine, like, let's say it's 2, for example, it's 1 minus 2 here. So it produces 1 over B to the 1. Well, we got to negate it. So it's P minus 1. And so this right here, this right here always goes to 0. This 1 over B minus P. The reason if you bring it down to the bottom, you have to negate the exponent. So what it is, if P is greater than 1, it looks like this. And this goes to 0. It becomes 1 over 1 minus P times 0 minus 1 over 1 minus P, A to the 1 minus P power. And so it ends up just being this on the right. And it's all because of that. It's all because you can think of the X is now on the bottom.
Or why'd you put it on the bottom?
Because it's not clear. Like, you would think of this as X to the 1 minus P. You wouldn't necessarily remember, like, why does that go to 0 as B goes to infinity? It's because when it's on the bottom here, like, you almost need an example. You like this right here. So imagine B is really X and P is 2. So this becomes 1 over X to the 2 minus 1, which is 1 over X to the 1. As X goes to infinity, what happens?
It goes 0.
It goes 0. And if I put a 3 there, I get a 3 there, or 2, the same thing. 4, 4, and so on. And even if it's 1.00001, when you subtract it from 1 point, all those, you still get a number that eventually goes, you know, to 0 to infinity. Even if it's like that, it still goes to 0 eventually.
Right.
And that's the idea.
Okay.
So like the answer, like just to finish it up here, this part right here is often written as 1 over p minus 1. You put the negative on the bottom, a to the 1 minus p. A is the lower bound of the integral, which I don't know what it is. Could be 1, could be 2, could be really anything.
Right. Or is the a to the 1 minus, is that supposed to be a p instead of a b?
Oh yeah, yes,
Okay.
yes, that's supposed to be a p. Yeah.
I guess I'm still just wondering why you put the b to the 1 minus p on the bottom.
Okay, so here let me start with that part. B to the 1 minus p equals 1 over b, but you have to negate the exponent here. And it comes from x to the minus n equals 1 over x to the n. Basically, when you swap positions, you negate the exponent. So more commonly, you're used to maybe seeing it like this: x to the minus n equals x to the n. So all I did is when I put a 1 over, I have to negate the exponent, which makes it 1 over b to the minus 1 plus p, or what is better is p minus 1.
Right. Okay. All right. I'm ready to.
All right, does that shore it up? Okay.
Yep.
All right, so let's see here. All right, so I don't really like the way this is written, but what they're trying to tell you to do is you're supposed to write this thing right here, and it's as a ratio of integers. So like what you're supposed to see is that this part right here is point. Well, let me head a moment to this. So it's point. Do this one. 0, 3, 1.
I think I remember we wrote it as 2 plus 8 over 10.
That's right. Yeah, that's
3 over 100. Right.
Well, so the repeating part is what you have to write as a series. And it's because it's 0.031, because it's 0.0313131, you have to like move this over, and that puts a 10 to the minus 1 there, times sigma 0.31 0.0031. So let me write this differently. 0.31 plus 0.0031 plus 0.123431, and so on. Okay, and this right here is a geometric series in here. Well, if you take 0.0031 and divide by 0.31, I believe you get 1 over 100. And then if you do the same thing, if you do 0.000031 over 0.0031, you also get 1 over 100.
Oh, okay.
Let me just double check that. So it's the repeating part that you care about. This one's harder because it's usually they just give you the like repeating part after the decimal. You have to deal with this 10 to the minus 1 to like move it over one spot, which is it's its own little wrinkle here. 0.0031 divided by point. Yeah, so that's 1 over 100. All right. Yeah. Okay. So this is a geometric series on the right here from n equals 1 to infinity, and because it's geometric, you know that the sum is equal to a1 over 1 minus r. Remember that from previous lessons, other stuff
Yes.
done? Okay, so your R is 1/100. A1 is your first term. So it's 0.31 over 1 minus 1/100. And that's all of the sigma. Okay. You still have to multiply by this 10 to the minus 1, which is really 1/10.
Mhm.
2 plus 8/10 like this, plus that.
Okay.
We should maybe do an easier one if you really think that this will be on the test to kind of build up to this one.
Uh-huh.
Because it's, and this one's tough. This one's really got a lot in it that's not straightforward.
Okay. All right.
And then you just simplify all this, on the right, it's 0.31 over 99 over 100. 31 is really 31 over 100 over 99 over 100. So this becomes 31 over 99 times a 10th. But then you get this 8/10, and then you get this 2 over here. You can see it's horrible. I mean,
Yeah.
you almost need to calculate this point, because to make a common denominator, you got to go to 990.
Yeah. That's not fun.
No. The key here though is the part that repeats. Like once you figure out the part that repeats, and this 0 in front is really the oddity. Like if you could just ignore that for the moment and accept that it's 10 to the minus 1, this is what you do in almost every one of these problems. You write it out, however many, whatever the repeating part is, you write out, then you add the zeros, repeating part, add the zeros, repeating part. Because you can see this first 0.31 slides over the 0 zeros, then that 0.3131 slides over these zeros, and so on. And then it's always geometric. It always converges, and you use the infinite sum formula to get the value, and then you add that to the other stuff.
All right.
Okay. Do you want to do any other ones like that, or do you want me to move to 18?
There's one like that in my notes. I'll just look at that one.
Okay. So 18 is convergence or divergence. Yeah. All right. So whenever you're given a problem where it's recursive, some recursive sequences can be turned into non-recursive ones. And then you can actually do some of the stuff we've been talking about. So you basically have to let's be like, okay, n is 1, that's 3. When n is 2, it's minus 1/2 times the previous one, so it's minus 3/2. When n is 3, it's minus 1/2 times the previous one, which becomes 3/4. And then when n is 4, it's minus 1/2 times the previous one, which is minus 3/8. And this is probably enough to figure out whether there is n equals 2, is to see like, well, what is this? Is there a formula? I guess we do have to find a general formula for this. So let me write them out. It's 3 over 1, 3 over 2, 3 over 4, minus 3 over 8. So what are some things that you notice about this?
It's alternating from positive to negative.
Okay, good. Yep. What else?
It's going up by multiples of 2.
Powers of 2 on the bottom.
Yeah.
And then on the top, like, what is the number?
3.
It's always 3 on top. So that's enough to write a formula. So an equals, it's always 3, but then it could be minus 1. Now, is the first one negative or is the second one negative?
Second one.
Now, according to our formula, though, a1 if you put n here, this gives you a negative. So you have to either go n plus 1 here to get it to work out right. Just to get the power where you want it. And then on the bottom here, it's 2. And then if you put n here, well, 2 to the power of 1 gets you that one there. So it's all this one's n minus 1. And then maybe to be consistent, you might say, let me let me actually really make this one n minus 1 also.
Does it matter?
For look, it could matter. No, I mean, no, it doesn't matter, but however, if you wanted to do this the most like compact way, you could then write this as 3 times minus 1 over 2 to the n minus 1 power.
Okay.
That's like the most compact way you could see this. All right, so that's the formula, and then you take a limit as n goes to infinity. This is, I mean, this is geometric though.
Right.
And that means it's got a common ratio. The common ratio is the minus 1/2 here, but that doesn't help you. The limit as n goes to infinity of this thing, 3 times minus 1/2 to the n minus 1 power. The problem is it sits there and it alternates. It alternates minus 3 over 8, and then the next one would be 3 over 16. So it's weird. Like it actually jumps back and forth over the axis. Like it's further away, then it's closer, but then it jumps over, but it's closer to this. You know, that's, but every point like that. So kind of like this is not it, but it kind of like does this. So the limit is 0.
Right.
But notice it's not monotonic because you've got, you know, changes in it here. Like it's not always
decreasing.
right. It's up and down. So but the limit though, the limit of this thing is 0 because you can see it eventually becomes some number, whether it's positive or negative, over a really big number. And then converges. It converges to 0. I mean, that's the limit. That means it you can say converges to 0.
Okay.
So just my advice would be to be careful about what the instructor is actually asking for. You know, like maybe underline like, well, I better choose at the end.
Was that the last one?
Mm-hmm.
Okay.
Is there
Did we do for number 16? Did we do the second part of it where it if it's greater than 1 and it diverges?
Oh, let me find a reference for this because it's like you can't do it at 1 because the antiderivative changes, and that's this like sort of breaking point of it. But let me see if I can find one that's more mathy, we'll say. You're not going to be asked to prove it, I don't think. I mean, just guessing, it's usually you're using it. It's like when to use the integral test. Use it when the p-test is used to show convergence of something because it'll be just slightly bigger than 1, the p-value. But let me look here. Is your exam tomorrow?
Yep.
Well, so it's kind of the same deal. If so, you have to show it at n equals 1 also. So at n equals 1, it's the integral, or p equals 1. It's the integral, and they usually go 1 to infinity, which is what I'm going to do here. It's 1 over x to the 1 here, dx. And so this becomes the natural log of the absolute value of x from 1 to infinity. And this equals the natural log of infinity minus the natural log of 1, which diverges.
Right.
Okay. Now, if we do it when P is less than 1, so it's the integral 1 to infinity, 1 over x to the P. Okay. And what again, you get the same antiderivative as before when we did this. So you still have to take that minus P and add 1 to it over minus P plus 1. It's the same antiderivative for that, for P less than 1 and for P greater than 1, you get the same antiderivative. The difference though is when you evaluate it. So let me just rewrite this here, x to the 1 minus P over 1 minus P. So if P is less than 1, and consider an example, let's just say off to the side here that P is -2. What is what does this become up top?
3.
X cubed. And when you're evaluating that at infinity, x cubed goes to infinity. Right. So it's the same antiderivative. You just say kind of what you do is you show somehow you say if P is less than 1, you say the limit as B goes to infinity, because B is what you plop in there for x, B to the 1 minus P over 1 minus P, evaluated from 1 to P, you show that this diverges. And for P greater than 1, it's the same thing. We did this before. You show that this does converge. And it's kind of all has to do with like these numbers, like you just said, if P is less than 1, like -2, you get a cube up here. But if it's greater than 1, you get x to the -2, and then it goes to the bottom, and that's why it converges.
Okay, all right. I hate this rule is like opposite from all the other converging rules, where if P is less than 1 or anything's less than 1, then it converges.
I mean, I think like what you're more likely to see is something like somehow does the sigma 1 over x to the or n to the 5/4, because I think this was like one we did.
Yeah.
Does this converge or diverge? And you're supposed to be like, oh yeah, integral test 1 over x to the 5/4.
Answer key. She has an answer key over this whole review, and that's how she did it. But I was like, well, I could just see that it's greater than 1.
Right. So converges by p-test, integral p-test.
Okay. So I wouldn't even have to do the integral test.
Well, you should ask her.
Right, yeah.
And hopefully she doesn't say something like, well, you should know what to do.
Yeah. Right.
Is there anything else you'd like to look at?
Yeah, I want to go up to these it's further, it's the second page of the review packet with all the like tips to help you decide which test to use.
Yes.
Hang on, give me a second to think. For the fourth one, the fourth little bullet point.
With a little bullet point.
Yeah.
Let's see here. 1, 2, 3, 4. Okay, integral test.
Yeah, for the continuous positive and decreasing part.
Yes.
How could you? Because she wants us to show us doing that.
Ooh, so continuous is tough to prove.
Or just by looking at something, is there like a trick to like notice if it's continuous or not?
So continuous functions break when the denominator is 0. That's one way to look at them. So like let me go see what Lamar thing does for that. All right, here we go. Okay, so here's one that is the integral test. Okay, so when you look at this thing right here, if this was really 1 over x to the natural log of x, where does it break? Where is it bad? And you would say, well, I can only take the natural log of numbers greater than 0, so x has to be greater than 0, and I can't divide by 0. Okay, which is accounted for here. But past that, like you're okay, like this is good. So somehow in words you have to say that, well, if this was 0, if it was starting at 0, that's bad, but because it's starting at 2, all the bad stuff is not there.
So when when the denominator is 0, that's when it's not continuous.
Well, that's one possibility, yes.
Okay.
Yes. And that's, I think, what you're asking me to kind of like explain. It's not a great explanation. Like, to prove something is continuous, you have to prove that the limit from the left and the right equals the actual output at every point on the whole thing. I mean, we don't really, we just talk about continuity, but that means that at every point, the limit from the left and the right are the same as the output value.
All right. Okay.
So that's where a sketch of this really helps.
Uh-huh.
I don't know how, like, I wouldn't know how to graph this if I were a calculus student again. I'd be like, I don't know. But
Yeah.
you could make me make a few guesses for that. Oh, another problem here is the natural log of 1. Natural log of 1 is 0, so that is a divide by 0.
Right.
So it's not that x is great, it's that you're okay from 0 to 1, and then x greater than 1, you're okay. So in interval notation, something like this. And that's why it's 2 and not 1, because it breaks at 1. So
Right. Okay.
it's like, well, what does this thing look like? And I have a feeling it's just going to look like this. So a graph could help you to figure out and say, okay, that's continuous because the graph.
For the most part, in these sum problems, are they going to be continuous?
Yes.
Okay. So I shouldn't even have to worry about it.
Probably not. The ones that are not continuous are probably going to be the alternating series ones, because they move back and forth from positive to negative.
Mhm.
That would be one to worry about.
Okay. What about telling if something's positive or not? I feel like that's a dumb question.
Well, I agree. I agree. How do you show something is positive? Well, 1 over n is always positive,
Right.
because 2 to infinity is positive. So that's positive. That's positive. I don't know how you and then natural log of n is greater than 0 when n is greater than 1, which is the case here.
Mm-hmm.
So therefore 1 over natural log of n is also greater than 0.
Right.
So here, okay, like you probably did this in calculus 1, but it's like, if n is greater than 0, then you can say 1 divided by n must also be greater than 0.
Right.
And if natural log of n is greater than 0, then you would say 1 over natural log of n must also be greater than 0. One leads
Right.
to the next.
Right.
It's more of a word thing. Like, and that's why I think you may find yourself writing out like this to explain.
Okay.
And then decreasing, well, it'd be good to show a few points, but you don't have a calculator, so you don't know what the natural log of like 2
Right.
is.
Yeah.
But a graph kind of shows everything. It shows that it's continuous, it's positive, and it's always decreasing.
Right. Okay. Now for I think that's it.
This I'm going to send you a link to this the Symbol Lab series solver. I used to use it a lot, and it actually tells you which test it uses, but it doesn't always use it sometimes defaults to the one that's easiest for the computer.
Mm-hmm.
But you might try with some practice problems throwing in there and seeing if like
Mhm.
kind of guessing like, hey, is this what test did they use?
Right.
And maybe that will help your studies.
Okay. All right. That's it for me.
Great. Well, thank you so much for being flexible with me today. It actually helped another student out. They were really in desperate need. So
Yeah, no
I
problem.
was able to thank you for letting me accommodate them. Good luck on your exam, and I'll see you next time.
All righty. Thank you.
Have a great night. Bye.